Good day, everyone. It is great to be able to speak to you today. In the presentation today, I'd like to share with you our paper Semantic Routing Fly Racing Network for Semantic Human Matting. We are from Dalian University of Technology, City University of Hong Kong, Wongsing Technology and Pengcheng Laboratory. In this presentation, I will first introduce the background of our work and the contributions of our work. Then, I will introduce the methodologies, including our network, which contains Semantic Addition module and Fly Elimination module. In this section, I will also introduce our last function. Next, I will give an introduction of our human matting dataset, and I will compare the experimental results of our method with some existing human matting methods. I will conclude our paper at the end of our talk. Okay, let's move to the first sections. Semantic human matting tries to estimate the opacity of objects in human images. Mathematically, given an input image, the matting problem can be formulated as this formula, where A, alpha, F and B are alpha mat, foreground, and background, respectively. Trimap-free human matting tries to accurately estimate the opacity of objects in images with only image as input. Trimap-free human matting is the future development trend of matting. It is different from previous trimap-based matting. It is because trimap-free matting does not need any extra input. The extra input is always very different to obtain in the real-world applications. Trimap-free human matting is also different from segmentation or saliency detection tasks, which aims to predict the binary mask. They only need classify the foreground and background pixel. In this task, pixels can be classified into three categories: foreground pixels, background pixels, and mixed pixels. And the mixed pixels need be more accurately estimated, as it contains the visual information from both foreground and background. A good matting result of image can more naturally separate the foreground object from the background in an image than a segmentation or saliency detection result. It is a very important technique in image editing applications. Now, it is not only used in film production for creating visual effects. With the rapid development of WE media, it becomes a common tool for the general public. Addressing human image matting without trimap is very challenging. The latest methods rely on estimating a segmentation map or a pseudo-trimap to constrain the matting process. However, their matting accuracy typically affects by the errors in these auxiliary maps. Motivated by recent flaw correction approaches, we propose a novel neural approach to address this problem. We first train a model to directly compute an initial mat, of which the errors are further detected by a flaw detector and corrected by refinement process. Our method, named Semantic Routing Fly Racing Network, SafeNet, has two novel modules: a Semantic Addition module, SAM, to enrich matting features with human semantics by an attention mechanism, and a Fly Elimination module, FEM, to correct errors in the defective mat regions. To facilitate the learning process, we have further constructed a large human matting dataset containing 4,722 unique foregrounds with fine annotations. We also conduct extensive experiments to demonstrate that our SafeNet outperforms most of existing trimap-free human image matting methods. As shown in this figure, our human matting pipeline consists of three components: a backbone network, a semantic addition module, SAM, and a Fly Elimination module, FEM. Given an input image, the backbone network first produces an initial alpha mat. This initial mat is then fed into SAM to enhance the semantics. Next, FEM takes the initial mat and the semantic enhanced features to predict the first refined alpha mat. The first refined alpha can then iteratively feed into SAM and FEM. And finally we have an output alpha mat. These figures show the detailed description of our semantic addition module, SAM, and a Fly Elimination module, FEM. We leverage two losses to train our pipeline. One is the alpha prediction loss. We also provide a benchmark. Some examples in our dataset. The examples from the left to right are the example of single frontal subset, single pose varied subset and multiple subset, respectively. Here are our experiment results. We achieve SOTA of semantic human matting. Our method achieves accurate figure extraction and detailed prediction. In this paper, we have proposed a novel semantic routing fly racing network, SafeNet, for semantic human matting. It first predicts an initial alpha mat with a single model. It then strengthens human semantics and erases erroneous regions in the initial alpha mat. In SafeNet, a backbone network is used to predict the initial alpha mat, and two novel modules, Semantic Addition Module, SAM, and Flaw Elimination Module, FUM, are exquisitely designed to predict a finer alpha mat from the initial mat. Experimental results have shown that the proposed method performs favorably against the state-of-the-art methods. In addition, we have also built a fine annotated dataset for semantic human matting, which contains 4,729 unique foregrounds.